Analysis of covariance examines the dependence of a continuous variable y on factor variable x2 when a continuous covariate, in this case x1, is taken into account. So in our model, x2, our factor variable, can take on two values, 0 or 1. And x1 is our continuous covariate. And sometimes x1 is called a confounding variable because we want to eliminate the effect of x1. We're mainly interested in the effect of x2 on our continuous dependent variable y. All right, let's take a look at this left-hand graph over here. We have y along the vertical axis and we have x1 along the horizontal axis. Now, we have sample points represented by the black and the blue points. The black points are the x2 equals 0 group, and the blue are the x2 equal 1. So this is the black or x2 represent x2 equals 0, and the blue x2 equal 1. And notice that these have an upward trend, that the sample points have an upward trend, which is a reflection of the dependence on x1. Now the model assumes a linear dependence of the expected value of y on x1 and x2. So let's see, when x2 equals 0, then this linear dependence is visualized in this black line. So let's take a look at that. Okay, so this black line has equation expected value of y is equal to beta 0 plus beta 1 times x1. All right, so beta 0 is indicated by this black box over here. Beta 0 is the y-intercept of the black line. And we see here's the value of beta 0. Beta 0 is equal to 60. Okay. And the slope beta 1 we have right here. The slope is 0.56. Okay, now the blue line, okay, the blue line is the represents the expected value of y when x2 is equal to 1. And here we see this is the equation of the blue line. We see the y-intercept is beta 0 plus beta 2. So this, right over here, we have beta 0 plus beta 2. Okay, and that value is equal to, here's beta 0, here's beta 2. The sum is 154. So this value of the, represented by the blue box, is 154. Okay, so really what we're interested in is whether or not beta 2 is equal to 0. If beta 2 is equal to 0, then this distance is 0, and that means that the expected value of y when x2 is equal to 0 is the same as the expected value of y when x2 equals 1, or that there is no difference between the black group and the blue group. We see that beta 2 is not equal to 0 in this model. In fact, beta 2 is equal to 94. But in practice, we only have sample points available to us, so we want to be able to infer from our sample data that either beta 2 is equal to 0 or not. And if we infer that beta 2 is not equal to 0, then we conclude that there is a difference between our two groups, between the black group and the blue group. Okay, we also have sample lines. So our gray line is our approximation of the black line based on our sample data points. So we approximate beta 0 with estimate B0 and beta 1 with estimate B1, and we get this sample line, which is an approximation of our line representing the expected value of y, given x2 equals 0, and similarly for x2 equal 1, we have an approximation right here. Okay, that's given by this equation, b0 plus b2 plus b1 times x1. It is instructive to view entities representing both parameters and sample estimates in one visualization. And we'll see in the next video that we can resample from the same population by just pressing this new sample button, and we'll get a different sample estimates, and we'll be able to see how some samples will approximate the parameters very well and other samples don't approximate the parameters very well. Okay, we can also then change model parameters. We'll see that we can drag this black box and the blue box to change the intercepts, and we can also rotate the lines and get different slope values, so we can change the parameters, and we can see how changing the parameters sometimes gives us a model that's not significant. We'll look at this over here. Sometimes this is significant, sometimes it isn't. And we'll be able to visualize what a significant model looks like and an insignificant model looks like.